MLX tool for the public census income dataset. Again, this dataset. Hello and welcome to the demo, building a classifier using AutoMLX. So in this demo, we will build a classifier using the Oracle AutoMLX tool for the public census income dataset. Again, this dataset is from OCI machine learning repository, and this is a binary classification dataset. Again, we will explore the various options provided by the Oracle AutoMLX tool, allowing the user to exercise control over the AutoML training process, and then we will evaluate different models trained by the AutoML. Again, for the Conda environment, we will be using Oracle AutoML and model explanation for Python 3.8, and the version is 2.0. So again, data analytics and modeling problems using machine learning are becoming very popular. And again, it often relies on the data science expertise to build accurate ML models. Such modeling tasks primarily involve the following steps: pre-processing the data set, which involves cleaning, imputing, feature engineering, and normalization. Again, and then you pick an appropriate model for the given data set and the prediction task at the end. After that, you basically tune the chosen model's hyperparameters for the given dataset. So again, all of these steps are significantly time consuming and heavily rely on the data scientist expertise. Unfortunately, to make this problem harder, the best feature subset model and the hyperparameter choice widely varies with the dataset and the prediction task. Hence, we don't have a one size fits all solution to achieve a reasonably good model performance. So again, using a simple Python API, this AutoML can quickly jumpstart the data science process with an accurately tuned model and appropriate features for a given prediction task. Start up with setting up the libraries. Again, we will load the census income dataset. We'll go through different steps and processes involved in the AutoML, and then we will analyze and kind of compare different results which we get through this using this AutoML API. So first we will do a basic setup for the notebook. So in this step, we are doing nothing but running some magic commands to display matplotlib plot and to automatically reload modules. So again, in the next code block, you can see we have loaded different required modules such as gzip to compress and decompress files. Again, you have pandas, numpy, matplotlib, sklearn, cbond to perform different steps involved in ML lifecycle, like accessing data, pre-processing, visualization, again some mathematical operation, and any other such related ML related tasks. So after that, we import the AutoML library itself, and we basically import a init function from there. So moving on to next step, which is loading the census income dataset. So we will start by reading in the dataset from the OpenML repo. This code block uses the fetch OpenML fetch_OpenML function from scikit-learn to download the adult dataset from the OpenML repo. And the name parameter specifies the name of the dataset to download, and this as_frame parameter, this will return the dataset as a pandas data frame. So now once you have run these, let's look at few of the values in the data. So again, keep in mind the purpose of this data set was to predict whether the income exceeds $50,000 per year based on the census data. So you can see we have different columns: age, work class, education, and race, and so on. So again, as you can see, it contains a mix of numerical and string data, which kind of make it a challenging problem to train machine learning models on. But you will also see that some of these columns are incorrectly labeled as category type. So once you run once you run this particular cell block, this is nothing but the function d types, which it kind of checks for different data type of all the columns. You can see age is being defined as category. The other example which I can give you is hours per week. This is also defined as category. I mean, we can outright see that these are incorrectly labeled. but again, we will handle them in the later steps. Also, the dataset contains a lot of missing values. So if you run this particular cell block, so this cell block will basically find the percentage of missing values in different columns. So again, I mean, nothing to worry about these since Oracle AutoMLX solution automatically handles missing values by dropping features with too many missing values. And again, if it's still it's not too many missing values to drop in a particular column or a feature, it helps you fill in the remaining missing values based on the feature type. So moving on to next step, we will try to visualize the distribution of the target variable in the training data. So target variable is nothing but the income. So you can see here across the the count of, or the entries of rows, or the number of rows we have, we can see here these many these many rows have income greater than $50,000, and these many rows has income less than or equal to $50,000 per year. So the next step is basically to separate the predictions, which is labeled as Y variable, from the training data X variable for both the training and test data sets. Also, you will see that we have defined the train size as 0.7, which kind of tells you like we are going to divide this data set into 70% of training data and the rest of the 30% as test data set. So again, this training set will be used to create a machine learning model using AutoML, and the test set will be used to evaluate the model's performance on unseen data. So you can see these first few lines of code. It basically defines a list of column names that correspond to numeric features and then convert those columns in the data frame to integer data type. So what we are doing basically is taking care of these mislabeled columns, which you saw here. Like A's was category, again hours per week was category. So we are kind of correcting them and converting them into the integer data type. So in the later part of this code, you can see we are splitting the data set again. And again, the target variable or the dependent variable, which is the income in our case, that variable is transformed using the map function here to convert the greater than 50K and less than or equal to 50K labels to binary, basically 1 and 0. So basically, we are trying to kind of relate that target variable into a binary classification scenario. And again, the as type method here, as we just discussed, it will convert the data type to the integer. So on running this particular cell block, you can see here the outcome of the train shape and the test shape. So we have almost 34. We have exactly 34,189 rows for the train data, and these many number of rows for the test data set. Again, this is the number of column 14. So now we will move on to the core of this demo, which is the AutoML. So we will start with setting up the engine. Basically, we are trying to create a pipeline, a complete pipeline for AutoML. So this offers a function called init, which allows you to initiate the parallel engine. So again, by default, the AutoML pipeline using the Dask parallel engine, but again, you can use it. You can set it to use local, basically, which is nothing but the Python's multiprocessing library for the parallelism. So as you can see here, the number of jobs you have set is 2, and the engine is being set to the local. So we'll start with creating an instance of the Oracle AutoMLX. So it will provide you a pipeline that automatically finds a tune model given a prediction task and a training data set. And again, in particular, it allows to find a tune model for any supervised prediction task, for example, classification or regression, where target can be binary, categorical, or real valued. So again, the whole AutoML, this comprises of basically five main steps or modules, you can say. The first part is pre-processing. So as I have already mentioned, like AutoML takes care of a lot of pre-processing steps for you. So this AutoML will clean, impute, again, engineer and normalize features for you. Then it will move on to algorithm selection step, which will identify the right classification algorithm for our use case. This is a classification problem for a given data set, and this will choose among these many classifiers. So these are the available classification algorithms which we have. You can see almost all the prominent and standard algorithms are there: AdaBoost, decision tree, Torch, MLP, and linear SVC, logistic regression, XGB, XGBoost classifier, Gaussian naive Bayes, and all. Then next step will be adaptive sampling. In this step, you will select a subset of the data samples for the model to be trained on. This will automate the process of sampling subsets of the training data and updating the sampling strategy based on the performance of the candidate models. So basically what is happening here, as the new models are evaluated and ranked, the sampling strategy is updated to focus on the regions of the feature space that are most promising based on the performance of the previous models. So what it does, it helps to improve the efficiency of the search and can lead to the better models in the less time. So the next step is feature selection. You will select a subset of the data features based on the previously selected model, whatever you finally select from the adaptive sampling. And after that, you will tune the model parameters to maximize the score for the given data set. So this step is called hyperparameter tuning. I mean, many of these steps are very generic to the ML lifecycle. AutoML just takes care of all of them for you. So now the next step is train a model using AutoML. So again, the AutoML API is quite simple to work with. You will create an instance of the pipeline, and next the training data is passed to the fit function, which executes the previously mentioned steps. So you can see here you are creating an instance of the pipeline. So you are calling the AutoML.pipeline, and the task you have defined as a classification task. Then it can be other options depending on the task. And you're passing the training data set through the fit function, xtrain and ytrain. So since, as I mentioned, I have already ran all these code blocks for you to save some time. So you can see here, the dataset shape again, the pre-processing is being completed here, and what's the cross validation like? When you see CV5, this is typically a parameter that is used to specify the number of folds in the cross validation procedure. Again, you can read much more about the cross validation technique itself. And then moving on to it starts with running model selection. Before that, you can also see that SVC and K-neighbors classifiers are disabled for the dataset with greater than 10k samples or greater than 1000 features. So again, once you have model selection completed, you can see here the chosen model was LGBM light gradient boosting, so LGBM classifier. And you can see here the adaptive sampling being completed on various k folds, basically 5, 1, 2, 3, 4, and 5. And then you will start with the feature selection, and then you will tune the model. You will tune the model hyperparameters to get the maximum score. So this is the whole complete process which you are going through. And then model is then generated again, and that can be used for the prediction task. So the predict probability method here, this method is used to predict the probability estimates for each of the class on the testing set X test. So the resulting probability estimates are stored again in the Y probability variable for the positive class. So you can see here this is being done only for the positive class. And finally, you are using ROC AUC area under curve score scoring metric to evaluate the performance of this model on the unseen data, which was the X test. and this is your final score. That's is 0.91. I mean, again, so the AutoML API, this also kind of creates a summary of the whole optimization process for you. It gets logged in, and it usually consists of the information about the training data and again information about the AutoML pipeline. So you can find the information such as the selected features that AutoML found to be most predictive in the training data, and you can see here the selected features which this AutoML pipeline found important to the age, work class, education number, and so on here. Again, you find the selected algorithm, which that was the best choice for that data. So you can find the selected algorithm as LGBM classifier. Again, you have selected hyperparameters for the selected algorithm. So these are the selected hyperparameters which your AutoML pipeline came up with. So again, using the print underscore summary function, you can basically output all the different trials performed using under these steps. So you can see here the different algorithms, again how many samples in total, how many features, and mean validation scores, and then hyperparameters, again the CPU and memory metrics, algorithm selection. So we are using this code block to basically plot scores predicted by algorithm selection for each algorithm. So model selection trials, this is used in context of Bayesian optimization, which is again a method for tuning the hyperparameters of a model using a probabilistic model that captures the relationship between the hyperparameters and the performance of models. So you can see here this plot will show the score predicted by the algorithm selection for each algorithm. So you can see we are using this negative log loss. This is optimization metric, which is basically just a negative of the log loss function. So this means the lower negative log loss score will indicate a better performance, while a higher score will indicate a worse performance. So in our case, this LGBM classifier, this seems to be the best performing algorithm. Moving on, the next step is again adaptive sampling. So following the algorithm selection, this adaptive sampling aims to find the smallest dataset sample that can be created without compromising validation set score for the chosen model. And in this case, since no subset is found to keep the sufficient validation score, as you can see here, we will continue with the entire dataset. So the next step was feature selection. So after finding a sample subset, the next step is to find a relevant feature subset to maximize score for the chosen algorithm. So AutoML feature selection follows an intelligent search strategy, looking at various possible feature ranking and subsets and identifying that smallest feature subset that does not compromise on the score for the chosen algorithm. So basically the steps which are followed in feature selection is, first you start with choosing an appropriate algorithm for the feature selection. And again, there are various algorithms available for feature selection, such as recursive feature elimination, RFE, or SFS, or even PCA. Once you choose the algorithm that is suitable for the size and complexity of your dataset, you rank those features. And again, various techniques can be used to rank those features, such as correlation analysis, a statistical test, or as such. And again, once you rank those features, you search through possible feature subsets. So you start with the top ranked feature and systematically test different feature subsets using the chosen algorithm and cross validation. You then evaluate the performance of each subset and record the results. And you then move to the next ranked feature and repeat the whole process until all features have been tested. Once you have searched through all the possible feature subsets, you basically identify the smallest subset that does not compromise on the score. And you analyze the results of the feature subset search to identify the smallest subset of the features that achieves the best performance scores for the chosen algorithm. And once you have identified the smallest subset that does not compromise on the score, you finally evaluate the model. And basically, which model is giving you the maximum scores. So as you can see here, the feature selected were age, work class, education number, marital status, and so on. And these were the four features which were dropped during the feature selection trials. Again, this you can see the plots here. We can also use a confusion matrix to help us visualize the model's behavior. And again, note that the displayed confusion matrix represents percentages here. So basically, this confusion matrix function from the scikit-learn is used to calculate the confusion matrix, which is a table usually that summarizes the number of true positives, false positives, true negatives, and false negatives of the binary classification model. So these functions usually take three arguments. You have the true binary labels of the testing set converted to integers again. And you have again ypred, which is the predicted binary labels of the testing set. And thirdly, you have the labels. So the binary labels to use for the confusion matrix. The first label is used for the negative class and the second label is used for the positive class. So this resulting confusion matrix, this is then normalized by dividing each row by its sum to get the percentage of the examples in each class that were correctly or incorrectly classified. So this is the heat map kind of which shows you, the normalized confusion matrix. So again, you can see here the x-axis and the y-axis labels are set to prediction and actual respectively, and the other labels you can see it's whether it's greater than 50,000 or less than or equal to 50,000. So not only that, you can also kind of use AutoML in different ways other than what we saw above. So you can basically provide a specific model also, and this will kind of allow you to control what algorithms AutoML will consider during its optimization process. For example, you want only 3 or 4 out of these model, and which want them to be considered. So you can just pass those only models in this list here, in the model list here. For example, right now, let's say in this example, you are asking AutoML to only consider logistic regression. So it won't perform, the optimization process on any of the other models here. But you again have to make sure your models can belong to only these many models, because these are the supported models at present. So you can see here the ROC score again on the test data. Again, you can also use a custom validation set. So you can also specify a custom validation set that you want AutoML to use to evaluate the quality of models and configuration. So on running this code block, so which is nothing but you are using custom validation set here. As you can see, you are getting this particular score. Again, you can also increase the number of tuned models. So by default, AutoML only optimize the hyperparameters of the single best model from the model selection stage of the pipeline. However, you can optimize the hyperparameters of the top N models. So again, in this example, you can see you are telling the pipeline to tune the hyperparameters for the first best 2 of the 3 specified model. So this is the model list. Basically, this is step where you provide a specific model list to AutoML, and you ask the AutoML to optimize only the hyperparameters for the top 2 models here. So again, you can see the respective ROC score as in 0.855 here. So not only that, you can also specify a different scoring metric to the AutoML. As you would have seen, like we were using negative log loss for the classification. And again, I mean, this is the default also for the classification. Same for regression. The negative mean squared error is the default one for the regression. So the user can also choose any other scoring metric. So you have this list of possible metrics. So for binary classification, you can choose any of these. Again, for multi-class classification, you can again choose any of these. And for the regression, you can choose from this list. So for example, now we are asking the AutoML to optimize for the accuracy scoring matrix instead of the negative log loss. So you can see that on this, the model performs around the AUC ROC score on the test data is 0.855 again. So again, you can also create a user-defined scoring function to the AutoML. So So this is just a sample logic, like, you are defining your score function. You're passing the model, the training, and the X and Y, and your logic should be here, and then you return that score. And again, the scikit-learn has a make a scorer function, which will help you to create a user-defined scoring functions. So using leveraging the same scikit-learn implementation. So I mean, there is an implementation already for the F1 score function. We are using the same, and we will then create a scorer function and pass it to the score metric argument of the train. And here you can again see the AOC ROC score on the test data, which is around somewhat same, as compared to the previous AOC ROC score which we got on the test data. You can also specify a time budget to AutoML. So basically, the Oracle AutoMLX tool supports a user-given time budget in seconds. So again, given the small size of our dataset, we will give a small time budget of 10 seconds using the time budget argument in this case. You can see here we have defined this 10 second as the time budget. So you can see, it will run the complete optimization process of the AutoML. But if it's kind of go over this defined, this time limit, it will kind of reset the engine. I mean, basically you're getting a message that your time budget exceeded by this many seconds, and this task were timed out. In that case, it will kind of select the default default parameters for you. And in that case, this was your AOC ROC score. You can also specify a minimum feature list to AutoML. So this argument will ensure that these features, through the minimum features argument, these features are part of the final model that it creates. So as you would have remembered earlier, we kind of dropped 4 of the. Let me just go through that exact place where you do the feature selection trials. So as you can see, you have dropped these 4 features and you have kept the rest. And I mean, this was the the AutoML optimization process, and this feature selection trials kind of selected these many features and dropped these many features. So instead of that, let's say if you think you want a particular feature to be selected, not discarded for the whole AutoML process, you can pass those features in the min underscore features argument. So you can see FNL, GT, and AT country, which were actually dropped earlier, but you are here passing those 2 features to be considered for the AutoML process. So again, it takes 3 possible types of values. If integer, the minimum features could be between 0 to and the n features. If it's float, again, 0 and less than 1.0. Again, 1.0 is kind of disabling the feature selection. And if it's a list, you will just pass the name of the features to give. For example, how we have used here. This here concludes our demo on the building a classifier using AutoMLX.
Hello, I'm John Stainsby. In this short lesson, we'll take a look at hyperparameter tuning using ADS Tuner. Many machine learning models have parameters that are used to control the learning process. They are called hyperparameters and are not directly learned from the data. Hyperparameter tuning is the process of searching for the values of the hyperparameters by setting the values and optimizing a model. This is repeated for many different combinations of values, and then the best set of hyperparameters are chosen. The ADS Tuner has several hyperparameter search strategies that plug into common model architectures. They support user-defined search spaces and strategies, and they are functional with any ML library that doesn't have hyperparameter tuning. The ADS Tuner generates a tuning report that lists its trials, best performers, and statistics. To instantiate the ADS Tuner object, it requires the reference to the model that's being tuned. Optionally, we can specify the number of cross-validation folds to be used with each set of parameters and/or the search strategy. ADS Tuner needs a search space to tune the hyperparameters in, so you use the strategy parameter. This parameter can be set in two ways. You can specify the detailed search criteria, or you can use the built-in defaults. For the supported model classes, ADS Tuner provides perfunctory and detailed search spaces that are optimized for the class of model that's being used. The perfunctory option is optimized for a small search space so that the most important hyperparameters are tuned. Generally, this option is used early in your search as it reduces the computational cost and allows you to assess the quality of the model class that you're using. The detailed search space instructs ADS Tuner to cover a broad search space by tuning more hyperparameters. Typically, you would use it when you have determined what class of model is best suited for the dataset and type of problem you're working on. If you have experience with the dataset and have a good idea of what the best hyperparameter values are, you can use a custom search space where you pass a dictionary that defines the search space into the strategy. To tune the model, call the tune method while providing the observations and outcome values. The stopping criteria can also be specified with the exit_criterion parameter. ADS Tuner continues to search until one of the stopping criteria is reached. You can change the custom search space in three ways: adding or removing hyperparameters, or by modifying the range of existing non-categorical hyperparameters. In this lesson, we provided an overview of the ADS Tuner, its cross-validation and search space strategies, as well as exit criteria. Thank you.
Hello and welcome to the next lesson in the Oracle Cloud Infrastructure Data Science course. My name is Himanshu Raj and I'm a data scientist and senior training lead for AI/ML at Oracle. In this lesson, we will learn about evaluating ML models. We will discuss the process and the benefits as well as the different types of ADS evaluators. We can see that model evaluation comes after model training phase in a machine learning lifecycle. Models are only as useful as their quality of predictions. After architecting and training your model, we need different evaluation metrics to understand the performance of it. These evaluation metrics compare the performance across a series of benchmarks. The usual process is to hold a validation set labeled with target feature and then to compare the predictions returned by ML model. The next step is then to generate metrics which tells you how close are the predicted and target values. Basically, these metrics are set of functions that convert the output of your test data into an interpretable, standardized series of scores and charts. So what are the benefits of doing the model evaluation? The first is benchmarking, which helps to track and compare the performance of the trained model or models. For example, how the confusion metric looks like. Again, the choice of metric depends on the ML use case. For example, whether it's a binary class classification or a multi-class classification. The next benefit is to discover pitfalls. For example, why my model has a high accuracy and a low precision, or is my model guessing at random? Third in the list is understanding the trade-offs between various models. For example, model A performs well when the weather is clear, but is much more uncertain during inclement conditions. To help with the problem of model evaluation and selection, ADS offers the evaluation class, which is a collection of tools, metrics, and charts. There are three types of ADS evaluators. One for binary classification, wherein the output is binary, for example, 1 or 0. Another one is for multi-class classification, wherein the output is discrete, for example, colors. And last one is for regression, wherein the output is continuous, for example, price or length. We can also leverage open source methods such as scikit-learn for clustering in collaboration with ADS. Let's discuss about these three ADS evaluators one by one. These are some of the prevailing metrics for evaluating a binary classification model provided in ADS. You can, of course, refer the ADS talk to go through these metrics in more detail. You use ADS evaluator and ADS model class in the ADS package to generate these metrics. This code snippet demonstrates how to generate the metrics and charts. In this example, we have two classification models, logistic regression and random forest classifier. From estimator function takes as input a fitted estimator and converts it into an ADS model object. All the related metrics for the logistic regression and random forest models from the previous snippet can be shown using evaluator.metrics. You can see here the precision is 0.9024 for logistic regression but 0.8814 for random forest classifier. While evaluation metrics is used for showing all metrics, charts on other hand can be shown by evaluator.showInNotebook. There are various parameters which you can use. Perfect is one such parameter. If perfect is set to true, ADS plots a perfect classifier for comparison in lift and gain charts. You can add a custom metric as required using evaluator.addMetric. F2 score here is in the added metric. On the right are the charts associated with binary classification. Moving on to next slide, you can see lift and gain chart, precision and recall curves chart, and normalized confusion metrics generated here using ADS packages. So usually these are the charts generated by using ADS package, and this is how it looks. Moving on to multi-class classification metrics, these are some of the prevailing metrics for evaluating a multi-class classification model provided in ADS. You can see here Hamming loss, FN score, recall, ROC, AOC. Well, there are like weighted, macro, micro FN score. Same goes for precision and recall. Again, the metrics are very similar to that of binary classification metrics. You can generate the metrics and charts using ADS evaluator class, but here you have to pass the class labels in the class argument too in the from estimator function. As you can see here, 0, 1, 2, these are the class labels. Again, evaluator.metrics shows all the related metrics. Basically, you can see here the comparison between logistic regression and random forest classifier metrics, like how there are different scores for all these different metrics, and you can compare all of them like all together. You can also show different charts and plots as same as earlier using evaluator.showInNotebook class. You can see different metrics and charts, how it looks. On the right side you have the list of the charts. You can see there. These are some of the charts and plots from multi-class classification. You can see multi-class ROC curve, precision by label, again F1 by label, and multi-class PR curve. Again, going on to regression metrics, these are some of the prevailing metrics for evaluating a regression model provided in ADS. So you have R squared, explained variance score, mean squared error, absolute error, root mean squared error, and mean residuals. Again, you can use evaluator.metrics and evaluator.showInNotebook to show metrics and charts. You can also add a custom metric like the previous two evaluator here. Again, you can show metrics and charts in a table using the same functions and class as earlier. So we have basically 4 types of regression charts here. You can see the observed versus predicted. So basically a plot between observed and or actual values against the predicted values. Again, we have residuals, QQ plot. So it's quantile plot. It shows the residuals and quantiles of a standard normal distribution. So you can see that like it should be close to a straight line for a good model. So these are some of the benchmarks. Again, moving on to residuals versus predicted. The plot of residuals versus predicted values. Again, the next one is residuals versus observed. A plot between residuals and observed values. I hope this was a valuable lesson on learning how to evaluate models using ADS evaluators. We will see you in your next lesson.
First of all, let me congratulate you for reaching so far in the course. My name is Hemant Kahankari. I am a Senior Principal Training Lead at Oracle University. In this video, we'll talk about ADS evaluators. There are three types of ADS evaluators: binary classifier, multinomial classifier, and regression. These three evaluators simplify our task of calculating and plotting relevant metrics. So let me walk you through one small example for binary classification. As you can see, we import the ADS evaluator class. In this case, we create a binary classification dataset and split it. We also create a few estimators and fit it to a training data. We wrap the estimators with an ADS model class, and then we create an evaluator object using ADS evaluator class. We pass the models that we had created earlier. After that, we can simply use the evaluator dot metric statement to print all the relevant metrics. In this case, you can see the metrics are printed for two different estimators that we had selected: logistic regression and random forest classifier, and separate metrics are printed for the testing data as well as the training data. If we want to plot all the relevant graphs, then we can use the evaluator.show in notebook method. And as you can see here, all the relevant graphs are being plotted, including the confusion matrix. So as you can see, the evaluators make the job of calculating and plotting the metrics very, very simple. I would encourage you to take a few data sets and explore these evaluators. Thanks for listening.
Hello and welcome to the next lesson in the Oracle Cloud Infrastructure Data Science course. My name is Himanshu Raj and I'm a data scientist and senior training lead for AI/ML at Oracle. In this lesson, we will discuss about model explanations, which comes under the model validation stage in a typical ML lifecycle. We will discuss model explainability and its techniques. We will also discuss in detail about the first technique, that is of global explanation, and its related methods. The inherent and growing complexity of machine learning algorithms limits the ability to understand what the model has learned or why a given prediction was made, acting as a barrier to the adoption of machine learning. Model interpretation and model explainability is the process of explaining and interpreting machine learning models. So, what is explainability? The ability to explain the reasons behind a machine learning model's prediction. That is what called explainability. Again, what is interpretability? The level at which a human can understand these explanations, that's called interpretability. So moving on to model agnostic explanations. So these are the explanations which treat the machine learning model and feature pre-processing as a black box, instead of using properties from the model to guide the explanation. So let's talk about the explainability types now. So first in the list is global explanation. So this basically explains the general behavior of a machine learning model as a whole. We don't look at specific predictions in this case. Next comes the local explanations. It explains why a particular machine learning model would make a specific prediction. So these takes care of things locally. The third one is what if explanation. So this analyzes how changes in the value of features affects the model's predictions. So in this lesson, you will learn about global explanation, and in the next lesson, we will go over local and what if explanation. Let's talk about the global explanation techniques. There are three, and all of them are model agnostic methods. First one is feature permutation importance explanations. This method estimates and ranks feature importance based on the impact a feature has on a model's prediction. Next is feature dependence explanations. This one evaluates the relationship between feature values and model's target predictions. The third is accumulated local effects. It highlights effects that specific features have on prediction of the model by partially isolating effects of the other features. Moving on to first one, the feature permutation importance measures the predictive value of a feature machine learning model. It does this by evaluating how the prediction error increases when a feature is not available. Then a scoring metric is used to measure the prediction error. For example, F1 score is used for classification and R square is used for regression. So how it works? After calculating the baseline prediction error on the given dataset, the algorithm randomly shuffles the feature values. Basically, it is effectively adding noise to the feature. Prediction error of the new dataset is then compared to the prediction error of the original dataset. If the model relies heavily on the feature being shuffled to accurately predict the target variable, then the reordering would lead to less accurate predictions. If the model does not rely on the feature, then the prediction error would be unchanged. Model explanation in ADS produces three types of visualizations for feature permutation importance explanations, which are box plot, bar chart, and detailed scatter plot. Features which are located at higher ranks have more impact on the model predictions, and features at lower ranks have less impact on the model predictions. Additionally, the importance values represent the relative importance of the features. For example, in this Pearson's correlation plot, higher the number of two corresponding features, higher the rank and the impact. This example generates and visualizes a global feature permutation importance explanation on the Titanic dataset. The model was constructed using the ADS Oracle AutoML provider with XGBoost classifier. The x-axis here shows the feature importance. A longer bar indicates higher importance than a shorter bar. Each bar also has the average feature importance value along with the standard deviation of the importance values across all iterations of the algorithm. The x-axis shows the impact in a box plot that permuting a given feature had on the model's prediction score. The y-axis shows the different features in the relative importance order. For example, here this feature is more important than the other ones. The minimum first quartile, median, third quartile, and maximum of the feature importance values are also shown for each feature. Moving on to detailed scatter plot, it shows the feature importance values for each iteration of the algorithm. The x-axis again here shows the impact that permuting a given feature had on the model prediction score. The y-axis shows the different features in the relative important order. So feature dependence explanations is the first technique in the global explainer. It highlights the marginal effect that specific features have on the predictions of a model. So how does it work? First, you select a feature to explain from a trained machine learning model. ADS takes multiple values from the features value distribution from the dataset. Then it replaces every sample in the provided dataset with the same feature value from the feature distribution and then computes the model inference on the augmented dataset. This process is repeated for all of the selected values from the features distribution. If you have n different values selected from features distribution, then you will get n different datasets, each with the selected feature having the same value for all samples in the corresponding dataset. The model inference then generates n different model predictions, each with m values, one for each sample after the dataset is augmented. There are two explanation methods in ADS for feature dependence. First one is PDP, partial dependence plot, and the other one is ICE, that's individual conditional expectation. So for PDP, the average model prediction is computed across all augmented dataset samples. This results in n different values, each with an average of m predictions. For ICE, the model predictions for each augmented sample in the provided dataset are considered separately when the selected feature's value is replaced with a value from the feature distribution. This results in n into m different values. So let's discuss the types of PDP plot. These are one feature and two features. With one feature, it could be either continuous or categorical. Moving on to the plot itself, So this is the PDP, the partial dependence plot for the categorical feature. You can see here like the bar chart with each bar representing the average prediction from the model. And the x-axis shows the different values for the selected feature. For example, here this is like sex and this is female and male. Again, in the next case of discrete numerical feature, the x-axis shows the selected feature values and the y-axis shows here the average predicted target value. For classification task, predicted value is the prediction probability. For regression, it is again the raw predicted values. In case of two features, you can see a heat map here. X-axis and y-axis are the selected values of two features. Heat map color represents the average prediction from the model across all samples in the provided dataset. Moving on to IC plots, that is individual conditional expectation plots, they are either continuous or discrete or the categorical ones. So with IC plots for continuous feature, you can see here, every sample from the dataset, like when the selected feature is replaced with the given value, they are separate. The x-axis shows the selected feature values and the y-axis shows the predicted target value. For again classification tasks, the predicted value is the prediction probability, and for regression, it is again the raw predicted values itself. The median value can be plotted to highlight the trend. So this is the median value here. Again, for the categorical feature, this is an example of violin plot. You can see here the x-axis shows the different values for the selected feature, again in this case female and male, and the y-axis shows the predicted target value. So similar to partial dependent plots, that is PDP, accumulated local effects ALE is a model agnostic global explanation method that evaluates the relationship between feature values and target variables. It again highlights the effects that specific features have on the predictions of a machine learning model by partially isolating the effects of other features. So it is more robust against correlated features than the PDP. Again, it uses the conditional distribution of the feature of interest to generate augmented data, and this tends to create more realistic data than using marginal distribution. This helps to ensure that evaluated feature values, for example, xi are compared only with instances from the dataset that have similar values to the xi. I could be any number. So again, it calculates the average of the differences in model predictions over the augmented data instead of the average of the predictions themselves. And again, this helps to isolate the effect of the feature of interest. So how does this work? So first step is start with a trained model and select a feature to explain. So once you do that, you can compute the intervals of the selected feature to define the upper and lower boundaries used to compute the difference in model prediction when the feature is either increased or decreased. So for the numerical features, you can use the selected features value distribution extracted from the trained dataset. MLX selects multiple different intervals from the features distribution to evaluate. Again, the number of intervals to use and the range of the features distribution are configurable. In case of categorical features, since ALE computes the difference in model prediction between an increase and decrease in a features value, features must have some notion of order. This can be challenging for categorical feature as there may not be a notion of order, for example, race, eye color. To address this, MLX estimates the order of categorical feature values based on a categorical feature encoding technique. MLX provide multiple different encoding techniques based on the input data. For example, distance similarity. Compute a similarity matrix between all categorical feature values and the other values, and the orders are based on the similarity. Again, for each interval, MLX approximates the conditional distribution by identifying the samples that are in the neighborhood of the sample of interest, and then it calculates the difference in the model prediction when the selected features value of the samples is replaced by the upper and lower limit. Talking about the interpretation for the ALE plot, there are again continuous or discrete numerical features, and there is one for the categorical features. The x value in the graph is a numerical feature. The x-axis shows the selected feature values and the y-axis shows the delta in the target prediction variable relative to the average prediction. Hope this was a valuable lesson on learning model explainability in OCI data science, and we will see you in your next lesson. We have discussed about the first technique in model explainability, which is global explanation. We will now discuss in detail about the other two techniques. First one is local, which explains why the machine learning made a specific prediction, and what if, which helps to understand how changes in the value of features affects the model prediction. So let's start with the local explainers. So ADS has an enhanced version of local interpretable model agnostic explanations, which we call as LIME. So the key idea behind LIME is that while the global behavior of a machine learning model might be complex, the local behavior might be very simpler on the other hand. Local refers to the behavior of the model on similar samples. So how does it work? LIME tries to approximate the local behavior of the complex machine learning model with a simple, more easily interpretable surrogate model, such as linear model. If the surrogate model is able to accurately approximate the complex model's local behavior, then ADS can generate a local explanation of the complex model with the surrogate model. For example, when data is centered and scaled, the magnitude and sign of the coefficients in a linear model indicate the contribution each feature has towards the target variable. So now how to compute a local expression? The first step is to start with a trained ML model, and then you select a specific sample which you want to explain. Then you randomly generate a large space in a nearby neighborhood around the sample. Then you move on to generating prediction for each of those randomly generated local samples, and then fit a linear surrogate model on predictive values. So ADS LIME that has three sections basically. First one is model, the second is explainer, and the third one is explanations. Let's visit all of them one by one. Model section. The left column shows information about the machine learning model and the model's predictions, such as the true level value for the selected sample to explain, the predicted value from the black box model, and the prediction probabilities in case of classification or prediction values in case of regression. The right column, on the other hand, displays the sample to explain. For tabular datasets, this is a table, as you can see here, showing the feature names and corresponding values for the sample. In case of text datasets, this table will be replaced with the text sample to be explained. Moving on to the explainer section, the left column here presents the explainer configuration parameters, such as the underlying local explanation algorithm used, for example, LIME, the type of surrogate model, for example, linear, and the number of randomly generated local samples, for example, 5000, to train the local surrogate model, whether continuous features were discretized or not. The right column, on the other hand, provides a legend describing how to interpret the model explanations. The explanations section. So for classification tasks, a local explanation can be generated for each of the target labels, since the surrogate model is fit to the prediction probabilities from the black box model. In case of binary classification, the explanation for one class will mirror the other. For multinomial classification, the explanations describe how each feature contributes towards or against the specific target class. If the feature contributes against the specified target class, for example, decreases the prediction probability, it increases the prediction probability of one or more other target classes. The explanation for each target class is shown as a separate row in the explanation section. So the first part is feature importance. This section presents the actual local explanation. The explanation is visualized as a horizontal bar chart of feature importance values ordered by relative feature importance. The features with larger bars on the top are more important than the features with shorter bar at the bottom. Positive feature importance values to the right indicate that the feature increases the prediction target value. The negative feature importance values in the gray area to the left indicate that the feature decreases the prediction target value. The next section is explanation quality. So this section presents the quality by evaluating sample distance distributions and using evaluation matrix. So sample distance distribution, it basically presents the sample distributions used to train and evaluate the local surrogate model based on the distances, probably the Euclidean distances, of the generated samples from the sample to explain. This highlights the locality of generated sample spaces where the surrogate model, which is the explainer, is trained and evaluated. The evaluation matrix evaluates how accurately the surrogate model approximates the local behavior of the complex black box model. Multiple different regression and classification metrics are supported for the evaluation matrix. So moving on to the next technique, which is what if explainer. So this helps to understand how changes in an observation affects a model's prediction. There are basically two techniques in there. First one is explore sample and second one is explore predictions. So moving on to explore sample method, when this one is called via explore sample, it opens a GUI that has a single observation. The values of that sample can be changed. By clicking run inference, the model computes the prediction with the updated feature values. The interface here shows the original values and the values that has been changed. Explore predictions method. It allows the exploration of model predictions across either the marginal distribution in case of one feature or the joint distribution in case of two features. So explore prediction in case of one feature. So when only one feature is passed in as X, in this case you can see age, the chart shows the relationship between the feature X, the age, and the feature and the target Y, which is the prediction. In case of two features, if there are two features passed in, the values of the features are shown on X and Y axis, for example age and CRIM. The plot uses color in this case to indicate the value of the target. I hope this was a valuable lesson on learning model explainability in OCI data science. We will see you in your next lesson.
First of all, let me congratulate you for reaching so far in the course. My name is Hemant Gahankari. I am a Senior Principal Training Lead at Oracle University. In this video, we will talk about explainability and explainer objects. In order to use explainer objects, we have to use Oracle Auto MLX library. Oracle Auto MLX library is installed on a Conda Pack Auto MLX P38 CPU. In order to start using the explainer objects, first we have to initialize the Auto MLX engine. For that, we import the AutoML library. We use the init function. As usual, we have to get an estimator and fit the data, and then we can obtain an explainer object using the estimator, and then we can call upon the various methods to call upon the local as well as the global explainability methods. For more information on the explainability methods, you can refer to the ML explainer interface. Depending on the data set, more specific tabular explainer or text explainer is going to be written, and we will be calling upon the methods on those objects. I would suggest you to pick up a few data sets and explore using explainability and explainer objects. Thanks for listening.
Hello, I'm John Stainsby. In this lesson, I'll give you an overview of the model catalog. The model catalog provides a method to track and immutably store models. The model catalog allows organizations to maintain the provenance of models during all phases of the model's lifecycle. A model's artifacts include the model, hyperparameters, metadata about the model, the input and output schema, and a script to load the model and make predictions. These model artifacts can be shared among data scientists, tracked for provenance, reproduced, and deployed. A model's entry in the model catalog has the following components: a model artifact, that is, a zip file that includes the saved model, a Python script called the score.py file, and the runtime environment of the model called the runtime YAML, metadata about the provenance of the model including Git-related information, and the script or notebook used to push the model to the catalog. Model artifacts stored in the model catalog are immutable by design. To apply any changes to a model, create a new model. Immutability prevents unwanted changes. It ensures that any model in production can be tracked down to the exact artifact behind the model predictions. Please note that artifacts have a size limit of 100 megabytes when saved from the console and 20 gigabytes when using ADS, the OCI SDKs, and CLI. After training the machine learning model, you create the model artifact to save with your model in the model catalog. This creates centralized storage of the model and enables you to track model metadata. The score.py file contains your custom logic for loading serialized model objects to memory and defines an inference endpoint. The runtime YAML file provides instructions about which Conda environment to use when deploying the model using a data science model deployment. The model artifact validate.py file provides an optional series of test definitions that you can run on your model artifact before saving it to the model catalog. These model introspection tests capture many of the most common errors when preparing a model artifact. There is also a requirements text file that lists the third-party dependencies that you must install in your local environment before running introspection tests. The readme.md file gives you a series of step-by-step instructions to prepare and save a model artifact to the model catalog. We highly recommend that you follow these steps. It's important to note that any code used for inference should be zipped at the same level as the score.py file, or any level below the file. If any required files are present at folder levels above the score.py file, they are ignored and could result in deployment failures. So, your model artifact directory structure should match this example. Score.py contains two functions. The function parameters associated are customizable. You can define other helper functions in score.py that are invoked in predict. For example, you could define a data transformation function that defines custom transformations. We have provided various model catalog examples and templates, including the score.py files, in the GitHub repo. The purpose of the runtime YAML file is to provide the necessary runtime Conda environment references for model deployment purposes. This is required if you want to deploy your model by using the model deployment feature of the data science service. The model artifact version is the version of the artifact format. This is automatically extracted by ADS when the model is saved in the notebook session. The inference environment slug is the slug of the Conda environment you want to use for deployment and scoring purposes. In most cases, the inference environment is the same as the training environment, though that does not have to be the case. The inference environment type is the type of the Conda environment that you want to use for deployment and scoring purposes. There are two possible values here, either data science or published. The inference environment path is the path in object storage of the Conda environment you want to use for the deployment and scoring purposes. The path follows a syntax of bucket name at namespace / file path. Finally, the Python version is the version of the Conda environment you want to use for model deployment. The default version is Python 3.6. The supported versions are Python 3.6 and 3.7. In addition to score.py and runtime YAML, you can include any additional files that are necessary to run your model in your artifact. Now let's look at preparing your model metadata. There are 4 types of model catalog documentation. Model input and output schema. This is a description of the features that are necessary to make a successful model prediction. Model provenance. This is documentation that helps you improve the model reproducibility and auditability. Model introspection tests, which are a series of tests and checks run on a model artifact to test all aspects of the operational health of the model. And finally, model taxonomy, a description of the model that you're saving to the model catalog. Let's look at each of these in more detail. The schema definition is a description of the features that are necessary to make a successful model prediction. The schema definition is a contract that defines the required input payload that clients of the model must provide. Input and output schema is used only for documentation purposes in this release of the model catalog, and the output schema may not always be a necessary parameter. Here is an input schema example for you to review. And here is an output schema example for you to review. When you are working inside a Git repository, ADS is able to obtain your Git information and populate the model provenance metadata fields automatically for you. If you want to be able to reproduce your model, you need to know where the model was trained and which environment it was trained in, the source code, compute resources and training data, and the resulting features. Introspection tests are optional, and you can run them before saving the model to the model catalog. You can then save the test results as part of the model metadata. When you run the introspection tests, they generate a local test_JSON_output.json file. Model taxonomy allows you to describe the model you are saving to the model catalog, which is especially useful when working within a team who may not be as familiar with the model or understand important details from its name alone. The metadata fields associated with model taxonomy allow you to describe the machine learning use case and framework behind the model. The use case type describes the machine learning use case associated with the model using one of the listed values, like binary classification or regression, etc. Framework is the machine learning framework associated with the model using one of the listed values, like scikit-learn or TensorFlow. You can add the framework version as a free text value, for example, PyTorch 1.9. Algorithm is the algorithm or model instance class. This is a free text value, for example, cart algorithm. Hyperparameters are the hyperparameters of the model object in a JSON format. Artifact test results are the JSON output of the artifact test run on the client side. Custom model taxonomy means you can add your own custom metadata to document your model. These include a key and value, and optional elements like a category, which is the category of the metadata from a predefined list, and a description, which is simply a description of the custom metadata. Please note that the maximum allowed file size for the combined defined and custom metadata is 32 kilobytes. The model catalog is a centralized and managed repository of model artifacts. Models stored in the model catalog can be shared across members of a team, and they can be loaded back into a notebook session. Model catalog documentation contains model provenance, introspection tests, taxonomy, and input and output schema. If you've been following along since the beginning of this course, you'll know that like any OCI resource, access to model catalog is required to be set via policies. Different policies are available for the model catalog management and for invoking the endpoint. Policies are also required to allow the model catalog to access other OCI resources like object storage. Thank you. Hello, I'm John Stainsby. In this lesson, we'll learn about managing models in the model catalog, viewing models and their information, and editing models, as well as some other useful operations. Serialization refers to the process of converting a data object, like Python objects or TensorFlow models, into a format that allows us to store or transmit the data and then recreate the object when needed by using the reverse process of deserialization. The process of serialization is also known as marshalling in some of the object situations. There are different formats for serialization of data, such as JSON, XML, HDF5, Python's Pickle, and they're all used for different purposes. JSON, for instance, returns a human-readable string form, while Python's Pickle library can return a byte array. The serialization object has different classes. For example, if you have a PyTorch model, you would use the PyTorch model class. If you have a TensorFlow model, you would use the TensorFlow model class. ADS has model serialization for many different model classes. However, it's not feasible to have a model serialization class for all model types. The save method stores the model artifacts in the model catalog. It reloads score.py and runtime YAML files from disk. This will pick up any changes that have been made to those files. If ignore introspection is set to false, then it conducts an introspection test to determine if the model deployment might have issues. If potential problems are detected, it will suggest possible remedies. Lastly, it uploads the artifacts to the model catalog and returns the model OCID. You can also call introspect to conduct the test at any time after you call prepare. Using the generic approach, the prepare generic model function will help you convert any type of model into an ADS model object. ADS assists you in preparing a model artifact by generating standardized code that you modify to represent your use case. After you modify the files, you save the resulting ADS model object and the model metadata ADS generates to the model catalog. You can save your models by using three interfaces: the ADS SDK, OCI Python SDK, and the OCI console. Most commonly in data science, you'll interact with the OCI APIs via these interfaces. We'll now explain the options for saving models and managing them. Note that you can use the OCI Python SDK, the OCI console, and ADS SDK to programmatically save models. You can view, edit, move, delete, activate, or deactivate data science models. You can even add tags on the Tags tab. You can apply both defined and free-form tags to models by working with the Resources tags. In the Model Provenance view, the Training Resource tab shows the notebook session or job run that trained the model. You can select them to manage them. The Model Training Source Code tab shows the Git details, model script, and training script. The Model Taxonomy view shows the model taxonomy, description, and custom attributes. If there are associated model deployments, then they are listed so that you can select a deployment to manage it. When model introspection has been defined, you can view the tests that ran on the client side before you save the model to the model catalog by clicking score.py or runtime YAML. The status is shown for each use case test as success, failed, or not tested. We recommend that all of your tests are successful before you save the model. When input and output model schemas have been defined, the contents of the uploaded files are displayed in separate fields. You can review and copy the contents. Users can change the name and description of a model and then save the changes. If users have added metadata to a model, they can edit the provenance and taxonomy. However, they can't edit the input and output schemas or modify the model itself. You can move a model from its current compartment to a different one. For example, you may want to move a model to promote it from a development compartment to a production compartment, or change the visibility of the model. Models cannot be moved across projects. To activate a model, users can either click the model's name or the Actions menu and click Activate to change an inactive model to an active model. Deactivating a model updates its state to inactive. Inactive models can't be used in a model deployment. Inactive models are not deleted and can be easily reactivated. To delete a model, either click the model's name or the Actions menu and click Delete. Enter the exact name, which is case insensitive, of the model and click Delete to delete the model. Note that deleted models exist in lists for 30 days after being deleted. You can filter them out of lists using the state filter. Users can perform the following operations on models inside the model catalog. They can list models, edit some model metadata, but not the model or its schemas. They can move models across compartments and activate or deactivate models. Users can delete models, although they continue to exist in lists for 30 days after being deleted. And in CLI or SDK, the users can perform create, update, list, and delete operations on a model. Thank you.
Hello and welcome to the next lesson in the Oracle Cloud Infrastructure Data Science course. My name is Himanshu Raj and I'm a data scientist and senior training lead for AI/ML at Oracle. In this lesson, we will learn about deploying the ML models. We will discuss about the model deployment flow and the related architecture in the OCI data science. We will see the various components of the model deployment and will also learn how to create, manage, invoke, monitor, and deactivate or reactivate a model deployment. After the model training and evaluation process are complete, the best candidate models are captured in the model catalog, as you would have learned in the previous lesson. Depending on how you intend to consume the predictions, you can deploy for batch consumption or real-time consumption. For batch consumption, the prediction can be scheduled every hour, every day. For real-time consumption, a trigger would initiate the process of using the persisted model to serve a prediction. For example, deciding whether a transaction is fraudulent or not when payment is initiated, that requires a real-time prediction. Deploying machine learning library models as HTTP web endpoints serving predictions in real time is the most common way that models are productionized these days. Model deployments are a managed resource in the OCI data science service for deploying machine learning models as HTTP endpoints. Here is the OCI data science model deployment architecture. The client application requests the model deployed as HTTP endpoint using API calls. These deployed models are from a list of candidate models from model catalog. The service supports models running in a Python runtime environment, and their dependencies can be packaged in a Conda environment. Again, the model deployments can be integrated with the logging service. This optional integration allows you to emit logs from a model and then inspect these logs. The key components of the model deployment architecture are load balancer. A load balancer provides an automated way to distribute traffic from one entry point to multiple model servers running in a pool of virtual machines. VM instances pool. This is a pool of VM instances hosting the model server, the Conda environment, and the model itself. Next one is model artifact. This is the actual model file to load and its predict code for inferencing. Next one is Conda environment. A Conda environment encapsulates all the third-party Python dependencies like NumPy, Dask, or XGBoost that your model requires. And the last one is logs. The emit logs from the inference code to OCI logging. These are very helpful in monitoring and debugging. Let's move on to creating and invoking a model deployment. A model entry in the model catalog has two components. First one is score.py. It provides the instruction about using model for inference. And the second one is runtime.yml. This is a YML file documenting the runtime environment of the model. Like it has informations like versioning, model deployment parameters defined in it. Again, there are other deployment configurations such as compute, shape, number of instances, logs, and such. The snippet on the left shows the various configurations needed to be defined. So this snippet shows how to create a model deployment from the UI console. First, you enter your name for the deployment. Then you select the model from the catalog. Again, you select the compute shape and the number of instances here. Then you move on to selecting the logging service. And lastly, you select the load balancer bandwidth. So when estimating the required bandwidth of the load balancer, we recommend that you add an extra 20% to allow for estimation errors and sporadic peak traffic. So this is a tip on how to calculate your load balancer bandwidth. So for example, if the payload is 1024 KB and you estimate 120 requests per second, then the recommended load balancer bandwidth would be 1024 multiplied by 120 multiplied by 8 and divided by 1024. And since we are considering extra 20%, this is 1.2 and it comes out to be 1152 Mbps. This is the formula here. You can also deploy a model from model catalog using ADS. The .deploy method of the model deployer class is used to create a model deployment. Again, there are two ways to use the .deploy method. You can create a model deployment properties object and pass that in, or you can define the model deployment properties using the .deploy methods as shown here in this snippet. Alternatively, you can also use OCI CLI to create a model deployment using the OCI data science model deployment create command. This takes a configuration JSON files as shown here, where you define the deployment type and model configuration details. Again, an optional log configuration JSON file can also be added to access and predict logs. Once the deployment is completed and in active state, it can be invoked to generate predictions on the new data. This is done by sending HTTP requests to the endpoints. Model deployment in return sends an HTTPS response with the predictions. Invoking a model deployment means that you can pass feature vectors or data samples to the predict endpoint, and then the model returns prediction for those data samples. You can use the sample code from model deployment detail, which enables you to invoke the model endpoint using OCI CLI. Alternatively, you could also use the OCI Python SDK or the Java SDK. You can invoke the model using these two with the detailed instructions in the OCI console itself on the model deployment page. This example here invokes a model the predict endpoint, and you can't customize this timeout value. If latency is an issue for you, then using streaming inference is a better alternative. Again, you have to use base 64 encoding. Let's discuss now how to manage a model deployment. You can view, edit, and manage your model deployments from model deployment page in the project's UI console. It shows details such as OCID, compute configuration, and so on. You can view, access, and predict logs. Again, work requests provide you with the status of every operations which you have applied to your model deployment. Invokes enables you to invoke the predict endpoint of the model deployment. Again, when the model deployment is in an active state, you can change name, model, VM compute shape, instances, and others one at a time with zero downtime to your model deployment. When inactive, all changes can be made at once. Model deployments can be also deactivated and reactivated. Deactivating a model deployment shuts down the instances that are associated with your deployment. Metering and billing of the model deployment instances and the load balancer stops when a model deployment is deactivated. The deployment HTTP endpoints become unavailable, but the model deployment metadata is saved. A deactivated model deployment can be reactivated. The same model HTTP endpoint is available upon reactivation, and requests can be made to that model endpoint. Well, you can also delete a model. You can monitor the model deployment through logs and metrics. You can use OCI logging service to log important informations. Access log captures detailed information about the requests sent to the model endpoint. The predict logs comes from the score.py logging calls. You can monitor the health, capacity, and performance of model deployments with the built-in metrics using OCI monitoring. Model deployments has metrics for CPU utilization, memory utilization, and network utilization, which includes parameters such as request count, latency, and bandwidth. From the console, you can open the metrics page to view all the built-in metrics. You can also do the following with the OCI monitoring from the options menu. You can either dive deeper with each metric by opening the metrics query in the Metrics Explorer, or you can create an alarm based on the metric when crossing a threshold. Hope this was a valuable lesson for you to learn about model deployment in OCI data science. We will go through a small demo now to have a quick hands-on. Once you are in projects page in your OCI data science, click on your working project. In my case, this is TestDS. You can see on the left hand side, there are different resources such as notebook sessions, jobs, models, model deployments. Go ahead and click on model deployments. You can now click on create model deployment. In there, make sure you are in the right compartment. In my case, this is OCI data science compartment. You can enter a unique name for the model. It has a limit of 255 characters. If you don't provide a name is automatically generated for you. So let's go and enter a name here. I am putting test model deploy in my case. You can also provide a description for the model deployment. So this is to test model deployment. You can then select an active model to deploy from the model catalog by clicking select. In my case, you can see I already have an active model, RF classifier. So I'm going to select that one and submit. Once you select the model, you can go ahead and select the VM shape and the limits you want to apply to your model deployment. So I'm going to select the compute shape. So I'm going with number of OCPUs 1 and memory 15. You can also select the number of instances for the model deployment to replicate the model on. The more instances you have, the more load the deployment can handle by distributing the requests across the instances. So let's go ahead and select 2. Hit the submit. You can also enable the logging. It's an optional configuration. So go ahead and click on select. You can see the access logs and the predict logs here. So access logs, it captures detailed information about request, and as we discussed earlier, predict logs, it captures std out and std error from the predict Python code. So go ahead and select the log names and then hit submit. So in the show advanced options, you can also set the load balancing and tags there. So basically you can select the load balancing bandwidth in Mbps, or you can also use the 10 Mbps by default. So the recommended way to do this is the formula which we discussed. This is a payload size in kilobytes multiplied by estimated number of requests per second, and then multiplied by 8 divided by 1024 KB. So for example, if the payload is 124 kilobytes and you estimate 120 requests per second, then the recommended load balancer bandwidth would be 1024 multiplied by 120 multiplied by 8 and divided by 1024. And since we always